Now, figure 12 shows, okay, for lubricant flow through bearing. So figure 12 shows typical circumferential pressure, this pressure distribution, ito, at different sections of finite length bearings. The flow in this direction depends on the pumping action of the journal. For the pumping action sa oil. For the ideal bearing, it can be computed from the flow variable Q over divided by R C sub R N sub S L. Then value from table or curves, which is dimensionless, is equal to Q over R C R N S L, obtainable from table 1 to 4. That is the flow in. So where Q is a cubic inch per second is the needed rate of flow into the leading end of the film to conform to hydrodynamic requirements. Ito yung ipapasok ng oil flow rate. So ito yan. Circumferential pressure distribution. The curve level 0.05 L from the end of bearing. Where L is the axial length of the bearing perpendicular dito sa papel o sa screen. Thus, 0.05 L represents the distribution of pressure at the center of the bearing. So, itong 0.5, kalahati ng bearing. At ano niya, kung ang length mo is L, so sa gitna ng bearing, ito yung distribution mo. 0.5. Hindi naman para uniform yung pressure. So, for the flow, ito. Now, there is no side flow and leakage in an infinite bearing and no pressure gradient, but there is in bearings of finite length, and therefore a pressure gradient. The side leakage is computed from the flow ratio, QS over Q, table 1 to 4. So take note yung table 1 to 4, and then yung partial full bearing, 120 degrees, 80 degrees, and then. So ilalagay nyo yan sa solution kung anong table number para ma-identify kung tama yung ginagamit yung table. So values from table or curves, kasi meron tayong available curves, dimensionless, so QS over Q, which multiplied into Q gives the side flow QS, cubic inch per second, when the oil enters at ambient pressure in non-load carrying region, as it should in a simple hydrodynamic bearing. Kasi walang masyadong load doon sa side. Pero may magdi-leak doon. Diba? Pag na-compress yung oil, so kakalat yan. Energy increases of the oil. So habang ginagamit mo yung bearing, so magkakaroon ng heat yun. So friction. So the frictional loss in the bearing causes the temperature of the oil to increase. Delta T. So assume that all the frictional loss goes to increasing the lubricant temperature. Then the amount of energy into the oil is WC delta T, where W is equal to rho Q in pounds per second, is the mass rate of flow when rho is the density, pounds per cubic inch, C is the specific heat of the oil. So the formula, energy into the oil is Q is equal to WC times delta T sub O is equal to rho Q times C times delta T sub O with consistent units. For hydrocarbon oils from petroleum, the specific gravity will be close to 0.83, giving a density of 0.03 pounds per cubic inch at usual temperatures. The specific heat is about 0.4 BTU per pound Fahrenheit or 374 inch-pound per pound Fahrenheit. Keeping the units consistent, we have U sub F is equal to FW times pi times D double prime n sub s is equal to WC delta T sub O. In-equate lang. Yun na yung heat mo. Magiging energy of friction. So, is equal to rho QC delta T sub O. So, may yung D diameter mo is in inches. Kaya may inches doon. Inches sinabi ko. D double prime. So, U sub S equal to 0.03 times T734 times Q times delta T sub O. It is now 112 times Q times delta T, where it is assumed that all the oil has a temperature rise of delta T sub O. The overall average and where the inches is the general diameter in inches. Now, if all the oil that enters the film natakpan, which leaves the bearing, easy to arrange in partial bearing if new oil at a temperature T sub I degrees Fahrenheit is continuously introduced, and if the heat loss T sub O to the surroundings per unit of lubricant passing through is negligible, the latter equation can be used to compute the average temperature rise of the oil. Anyway. So, okay. The temperature rise variable rho C delta T sub O over P in table 1 to 4 is somewhat different. As the additional assumption here is that the mean temperature of the lubricant leaving the sides of the bearing Q sub S was equal to the average of the inlet and outlet temperatures of oil to the bearing. So on this basis, value from table dimensionless rho C delta T sub O over P, where rho is 0.03 pounds per cubic inch, C is equal to 374 inch pound per pound Fahrenheit, as given above for consistent unit, and where delta T sub O is the temperature rise of the circumferential flow, Q to QS, Q minus QS, and is larger than the average T sub O computed from use of equation. Therefore, it is more conservative prediction. Yan. Okay, so may note kayo dito parang note. Pag dito ka kumuha sa table, it is upper larger. Dito sa condition na to, ito kasi naging actual theoretical. Permissible minimum film thickness. Merong by suggestions. Kasi hindi pwede maging zero yon. Yung film thickness mo, yung thickness ng oil mo doon. Di ba yung pinakamanipis doon? Di ba yung oil? Tawag doon film. Data on design values of bits of O are not plentiful, so that in exceptional cases, in a particular situation, experiment may have to be conducted to determine safe limits. Correlates suggests H of O as 2.0001 inch as a minimum commercial limit. For finely bored small bronze bushing, H of O is 0.00075 inch for commercial overheated bearing. The initial suggests 0.0004 ang the initial suggests H of O from 0.0004 inch to 0.006 inch for 5 inch to 10 inch diameter. Diesel engine bearings speed 500 to 1 to RPM. Norton proposes H of O is equal to 0.00025 D each as a rough rule, where D is the nominal diameter of the journal. So, di ba, kailangan hanap ka ng reference. Fuller says that for medium speed, that is 500 to 15 RPM, Babbitt bearings on electric motors and generators H of O may be 0.00075 inch. For larger shafts at high speed, 1,500 to 136 RPM, Babbitt bearings pressure oil feed, the H of O is equal to 0.003 to 0.005 inch. For automotive and aviation reciprocating engines, bearings with fine surface finish, H of O is equal to 0.0001 to 0.0002 inch. But a filter to remove solid particles that's enough for more than or equal to 0.001 inch to damage the surface is necessary. So, kailangan may filter. So, the surface for better grades of bearing may be finished to 32 micro-inch RMS or below. Now, the clearance ratio, CR over R. Ano yung mga typical values? So, although the limits of the clearance and clearance ratio are largely determined by manufacturing criteria, one may come closer to some desired optimum condition with little or no extra cost if one knows what optimum he desired. A long-standing rule of thumb is a clearance ratio of 0.001, but evidently this value will be the best value only coincidentally, not always. So the minimum permissible value of CR over R as for H of O is dependent in some degrees on the bearing surfaces. So table 5 may be helpful as a guide to practice. So check nyo yung table 5. Ano yun? Mga shaft diameter and application. And the value. Okay? Hindi na natin isa-isahin. Now, length to diameter ratio. So may rules din. At may rules sa dimensioning. Niels concluded some time ago that L over D is approximately 1, say 0.8 to 1.3. Was a good compromise for the general case of hydrodynamic bearing. And nothing is happened to change this conclusion. Yeah. Thus, ratios of L over D greater than 1.5 are less common today than formerly. However, bearing with L over D less than 1 are often used for a reason. Say, the need for compactness as in V8 automotive engine. So for a particular diameter and clearance with a certain load and general speed, it can be seen that as L over D decreases, the minimum film thickness decreases, perhaps rapidly below L over D is less than 1. So figure 13, yung L over D ratio and the minimum film thickness, and then yung mga angle niya, yung partial bearing. So the film temperature increases perhaps rapidly for L over D below 0.5. The power loss decreases, and the amount of oil flow hydrodynamically pumped through the bearing decreases. As L over D decreases, the eccentricity ratio increases with decrease of film thickness, and the approach of the general surface to the bearing surface soon becomes dangerously close. Figure 13 suggesting a revision in some of the design assumptions. Fuller gives the following L over D values as typical of practice. So, sa turbo generators, mayroong 0.8 to 1.5. Gasoline and diesel engines, main and crank pin is 0.3 to 0.8. Generators and motors, 1.2 to 2. Shafts with self-aligning bearing is 3 to 4. Machine tools is 2 to 4. Railroad is 1.2 to 1.8. So, dito kayo tatingin sa mga books, handbooks, at yan mga tamang mga value. Yung mga typical use. Okay? Kung minsan sa ngayon, yung mga online na mga lecture, na-assume na lang nila. Titinginin dito, kukuha sila ng yung iba, tumitingin, yung iba, basta lecture lang. So, yung value, double check nyo lang yung mga value ginagamit. Okay? So, doon sa generator, makita mga generator dito, minsan, tingnan mo kung may foundation, wala. Sabihin ng iba, yan na sir yung pad. Ang tawag doon generator pad. Generator pad. Pinapatungan. Pero tingnan mo sa ilalim noon, walang foundation. So dapat meron yun. Kaya maiingay ang natin dito. Kasi meron nakita kong lecture doon nga na yun ang ginamit lang. So ang totoo, sa foundation, merong rules. Times 3 yung foundation mo. Times ang weight ng foundation. Times 3 ng equipment. May range yan. May 2.5 or 3 to 5. Meron namang 5 to 10 pag reciprocating. So hindi nasusunod yan. Kaya maiingay. Andiyan naman ang epekto. Sabihin nila, normal, generator yan. Okay? Hindi yan normal kasi wala sa design. So, heat dissipated from the bearings. So, mainit yan. So, many bearings are made with an integral supply of lubricant. As for example, a ring oil, figure 14, or chain oil or collar coil, figure 15. Bearing in which there is a local sump for lubricant storage. So, meron silang storage yan sa bearing. So, hindi lang doon sa clearance lang doon. So, meron po siyang stackan. This type of bearing can be designed to deliver adequate oil for hydrodynamic needs, but it must be possible for such bearing to dissipate all the frictional loss to the surroundings without an excessive temperature rise. Let the heat loss Q be given by F sub CR, A sub V, and delta TV in foot pounds per minute. Now, the heat loss to moving air is greater than this, up to 10 times greater according to some reports in the literature. So ito yung heat loss mo sa anticipated from the bearing. Frictional loss. So the heat loss to moving air is greater than this. O ganun yan. A sub CR is equal to 0.516 foot-pounds per minute square inch per Fahrenheit at 500 feet per minute is speed of the air. The average temperature rise of the oil, delta T sub OA, will be greater than delta TB of the bearing surface. How much greater depends on the method of lubrication and the construction of the bearing. This is the surface temperature minus the ambient. Ito, delta T, difference ng surface temperature. Difference of temperature ng oil. So, where H sub CR is the heat transfer coefficient for the bearing surface. Input mass per minute square inch Fahrenheit. A sub B to okay, balikan natin to. Ito, the heat loss to moving air is greater than this. Ibig sabihin, lakas ng hangin. So dito, normal lang. So, delta TB is the temperature rise of the bearing surface above ambient temperature. Okay? And tama kasi heat transfer. Okay? Ito naman is temperature rise of oil average. Sa MCP, delta T mo yung gagamitin. Okay? So, dito, this is at 500 speed. Kung may speed, kung wala ito, still air. So an old rule of thumb says to allow a heat loss in the still air of 2 BTU per hour, that's square foot of degrees Fahrenheit, which convert to the units of HCR as 0.18 foot-pounds per minute square inch in the still air. So hindi lumangin kung hindi tubig. Pag maparos. Pag maparos, yung isa, 0.56. So yun ang pagkaiba nitong HCR. Diba? Kaya reviewin nyo. So the following approximation adapted from Fuller may be used for temperature ranges likely to be reasonable. So ito yung proportion. Oil ring bearings, still air, delta T sub of OA is equal to 2 times delta TB. Oil bath bearing, still air, delta T sub OA is equal to 1.3 delta TB. Waste back bearing, still air, delta T sub OA is equal to 2.5 times delta TB. Now, for ring oil bearing, in 500 feet per minute air, delta T sub OA in terms of delta TB is some 15 to 20% greater than in still air. So, multiply mo to. Okay. Yan. Kasi, minsan, may application tayo ng bearing outdoor. So, outdoor, ibig sabihin, ito ang gamitin mo, 500 feet per minute. Pag indoor, so dito ka sa still air. So, nag-guess nyo yung application. So, itong 2 BTU per hour, narulog ito yung sa still air. So, any surface na may temperature, surface temperature, saka yung ambient niya, kung yung difference, multiply mo ng area times mo ng 2, that is the estimated heat loss in BTU per hour or watts. Pero may actual to, yung mahaba ang solusyon sa heat transfer. Lalabas doon, para malapit sa 2. 1.9, 1.8, 2.1, ganun lalabas. Kaya ito lang, rule of thumb lang is 2. Okay, ginamit din to sa board exam sa power plant namin noon. Yan, walang value. Hindi yung given na 2. Kaya yung iba, siyempre yung iba, exhibition para makuha mo yung value ng 2. Pagdating sa reviewer, 2 lang pala ginamit. Yung sa akin, exhibition lang. Kaya naging 1 point, naging 1.9. So, ginamit ko doon yung mga formula na sa pipe, sa ganun. Transfer pipe yun eh. So, sa reviewer, ito lang ginamit. Pero, hindi na masabing tama yung reviewer kasi yung siyempre, shortcut yun. So, di natin alam kung approve dun sa examiner yon o gusto niya yung mahaba. Okay. Wala sinabi. At least, ang kasabihan nun, pag malinis ang sulat mo at medyo kahit mahaba, malinaw at konti lang ang mali. So, tatama yung pag-check nila. So, consider yon. So, may points. Pero pag ang sulat mo noon, hindi naman kasi multiple choice, pataas, pababa, di maintindihan na nag-check, ito natapon na lang yung papel. Okay? Doon yun. Ngayon, computer na nga nag-check. Computer na nga. Shade lang kayo. Doon. Hindi na makikita yung sulat nyo kung pataas, pababa, kung di maintindihan. Yeah. Sa engineering nga eh, dapat malinaw. Ngayon, ano na lang. Shade, parang pindot-pindot na lang yan, digital. Okay? Kaya pagdating sa actual, hindi na alam yung gagawin kasi uli naman yung shading yung ginagawa mong design. Okay? So, ito, what area is of it to be used is also questionable. Yan, sa bearing. Ano yung area? So, for heavy construction, as ring pedestal bearing, Norton recommends ASO B is equal to 25 TL square inch, where DL is the projected area of the bearing. Note si Norton, hindi yan yung gumawa ng antivirus. Ano ba sa design yun? Sa mga bearing. Hindi yan si Norton yung antivirus. Nakaapo niya yan. Matagal na yan si Norton. So for light construction, A sub B is equal to 6DL will be safer. Fuller recommends an average A sub B is 12.5 DL for simple pillow block bearing, and A sub B is 20 DL square inch for pillow block bearings with separate shells. Considering the basic law of heat transfer according to which radiated heat is proportional to the absolute temperature to the fourth power, by compromises and considering that the temperature do not vary widely, we arrive at H sub R is 0.108 foot-pounds per minute square inch Fahrenheit as the unit rate of radiated heat, surface coefficient of radiation. This is the total H sub R plus H sub C is equal to HCR. Ito yung mga area. So ito naman is, ito is rule of thumb. So ito naman yung individual. Break natin yung HCR. Pagkuha ng individual. So although no directly applicable equations have been developed for the convected, in letter E hindi I, convected heat from bearing. The expression for round pipe exposed to a moving external fluid is helpful. H sub C D over K is equal to 0.24 times D rho V over mu exponent 0.6. Ito yung lang method. Where H sub C is the surface coefficient for convection, D is the pipe diameter, K, rho, and mu applied to surrounding fluid and are respectively the conductivity, density, and viscosity. The symbol group are dimensionless, and D rho P over mu is the Reynolds number. Okay, remember yung transfer. When the surrounding medium is air, this equation reduces to H is equal to C times P sub A exponent 0.6 over D exponent 0.4, where C is a function of the properties of air and experiment. Now, for meager experimental data, we choose C as 0.017 or H sub C is equal to 0.017 plus P sub A is 0.6 over this exponent 0.4 foot-pounds per minute square inch Fahrenheit. Now, the unit rate at which heat is convected. Where V sub A is feet per minute is the air speed, and D is the normal bearing diameter. Now, the total coefficient is then HCR is equal to HC plus SR. The value to be used in equation. So, if the speed of flow of air across the bearing can be estimated, this detailed procedure may be prepared. Yan. Sabihin, if the flow of air across the bearing can be estimated or given. Gamitin mo yung itong approach na to. Detailed procedure. Bearings located in the vicinity of the pulleys, flywheel, pulley, etc. may be assumed to have an airflow of 60 to 100 feet per minute. Yan. Pag walang available, so ito. Yan. Kaya pag nag-design ka, any available, kumplito o kulang-kulang, kung anong mga available mo, may magagamit ng mga equation. Kasi hanapin yan. Kung anong binigay sa'yo, apat na ano binigay sa'yo, gamitin mo yung apat. Pag dalawa binigay sa'yo, gamit mo dalawa. Pag kulang ka, mag-assume ka. Pag hindi, huwag ka mag-assume kasi merong binigay sa yung value. Kaya nga sa problem, gamitin mo yung ano yung nakalagay doon. Kung hindi naman magamit, so okay lang. Pero kailangan, kung available equation, gagamitin mo. Kasi pag nahuli ka, mali na yung solution mo. Diba? Gumamit ka ng isang equation na hindi gagamit ng isang value doon. Pero may available tinuro pala yung equation na gagamitin yun. O derive, pwedeng magamit. Or may effect. Kung walang effect, okay. Pero kung may effect, gamitin mo. Now, hit this same pa rin. Computing an operating temperature of the bearing is a process of iteration. So the basic procedure is to assume an average oil temperature, ito yung procedure, given the bearing dimension, etc. Compute the frictional loss, del use of F, and compute the heat loss Q. And if use of F is equal to Q, the assumed temperature is assumed to be the operating temperature. So tama yung trial mo. If use of F is not equal to Q, try another oil temperature. Iterate until the desired agreement is achieved. So ito yung paggamit ng mga equation na yan. Ito. Diba? Check nyo yung solution manual ko. Meron ng mga pag-solve nito. Okay, hanapin nyo itong topic doon. Sa mga problems and solution. Magamit nyo yan kung paano ginamit yung mga equation na to. Okay? Now, operating temperature. Kanina, dito is computing. Ito naman, what are the operating temperatures? So, conventional design value of the oil PEM temperatures are 140 to 160. So, dito ka mag-assume lang. Or less. At higher temperature, the oil oxidizes more rapidly above 200 Fahrenheit. The temperatures of the order of 250 Fahrenheit would not be tolerated in industrial equipment unless there is a no reasonable alternative. In automotive practice, oil temperatures of some 350 Fahrenheit or more, thus oxidation is a significant cause of deterioration in this application. Some bearing material will lose considerable fatigue and yield strength at higher temperatures. Now, the oil flow for pressure feed. May hole ka doon. An oil hole at the midpoint of the cap may be the whole system, in which case the axial flow in 360 degrees bearing is given by Shaw and Mach. Q is equal to C R cubed P sub I over 3 pi times arctangent of 2 pi R over L times 1 plus 1.5 epsilon squared cubic inch per pound per the units are consistent. Mu is in range, P sub I PSI is the inlet gauge pressure, pressure paid, and the other symbol have the usual meaning. So the theoretical axial flow through a 360 degrees bearing with a circumferential groove is Q is equal to 2 pi R sub CR cubed Pi over 3 pi L times 1 plus 1.5 squared cubic inch per second. Paano? So mawawala yung arctangent kasi 360 degrees na to. So where the units are consistent. Yan. So E is equal to 1 minus h sub O over R is 1 minus 2h sub O over CD. Else is strictly the total axial load carrying length. Figure O17. Ito. Yung group is minus mo dyan. Okay? So, friction loss on cap. Since the pressure gradient in the unloaded part are trivial, Newton's equation for viscosity may be used to estimate the frictional loss in unloaded part. For a cap arc between 120 and 180 degrees, yung cap niya, the average thickness of oil film may be estimated. Its of average is equal to C sub R is 1 plus 0.74 E squared is equal to CR times 1 plus 0.74 times 1 minus H sub O over CR squared in inch, which is the value of S to be used. To illustrate, let E is 0.49, C sub R is 0.00392, and mu is 1.52 times 10 is -6 range. The peripheral journal speed B is 4,000 feet per minute or 800 inches per second. D by L is 9 by 10 inch. So H average is CR times 1 plus 0.74 E squared is 0.00392 times 1 plus 0.74 times 0.49 squared is 0.000462. And the area of lubricant being shared in 180 degrees is A is equal to pi dl over 2 is equal to 141.2 each squared. Then the F is equal to mu A B sub IPS over its average is 1.52 times 10 negative 6 times 141.2 times 800 inch per second yan na 800 divided by 0.00462 is 37.2 pounds. Then the use of F is equal to F P sub M is equal to 33 so 37.2 times 4,000 is 148,800 foot-pounds per minute, which is equivalent to a loss of 4.51 horsepower. Yeah. This is now the loss. Now, materials for building, ano yung mga materials? So, properties that are considered advantageous for building materials include conformability, which is low modulus of elasticity, which means a larger deformation per unit load. Compatibility, which include anti-welding property with respect to steel and screw resistance. Kasi pag didikit yun, so anti-welding dapat. Embeddability, soften up to allow foreign particles to layers to pass through the minimum film to be forced into the surface and thus to be removed from the oil film without scoring and wear. Next, low shear strength, capacity to be smooth easily. And compressive and fatigue strength, capacity to withstand the maximum height dynamic pressure and to resist bitter fracture or for repeated loading at whatever temperature it operates. Corrosion resistant, good heat conductance, nearly the same coefficient of thermal expansion as the material of the housing and journal, and as always, low cost. Most used are babbits and copper alloys. Communicating babbits materials, it's a bearing yan. So the babbits are either tin-based or lead-based babbits, depending upon which metal is the principal alloy. Babbits are relatively weak in all forms and lose strength rapidly with increasing temperature, with the result that they are used more and more in a thin layer, less than 0.04 inch and down to 0.002 inch on a steel backing. With their low fatigue strength, they are not satisfactory where the load is severe and variable, although the thinnest layer is done up. In 0.016 in thickness, normal load capacity thick film fabrication is about 1,500 psi. So the copper alloy used for building are mostly bronze, which are much stronger and harder than babbit. A copper lead mixture, 25 to 50% lead in a layer about 0.0 inch thick, has a good fatigue strength. Normal load capacity is about 3,000 psi. 10 bronze have a normal load capacity of 5,000 psi. Silver bearings for heavy duty are made by depositing a 0.02 to 0.03 inch layer of silver on steel, followed by a thin layer of 0.001 to 0.003 inch. Then 4 to 5% indium is electrolytically deposited and thermally diffused into the layer of the lead, yung materials. A cast iron bearing with a hardened steel journal has been found to be an excellent combination from the standpoint of wear and friction if thin film lubrication exists. However, cast iron does not possess embeddability and other virtues of a softer material that usually outweigh its low cost. Aluminum alloy have been found favorable for bearing in internal combustion engine and in other demanding applications because of good strength, conductivity, corrosion resistance, and low cost. But the mating journal should be hardened. A thin layer of babbit may be used to improve embeddability. Elastomeric materials such as rubber serve excellent with water or as lubricant and are widely used for shaft of ship propellers, hydraulic turbines, hydraulic dredges, pumps, etc. The soft rubber passes sand and grit without scoring a journal. Numerous materials are used for bearing with and without oil or water lubrication, including the wood, lignum vitae, and oil-impregnated oak, plastic, This is nylon, Teflon, phenolic resin, and ceramics and ceramics, ceramic, and metal. Okay, especially in unusually high temperature application. Truss bearing, yan, vertical. Yung poste mo, ganyan. Many rotating shafts, some vertical, are subjected to axial forces of significant magnitude, forces that must be balanced at a bearing called a truss bearing. The simplest type carries the truss on parallel surfaces, no wedge shape firm as on the end of the shaft, figure 19, or on collar, figure 20. Unless the oil is introduced into the bearing surfaces under pressure sufficient to support the load, boundary lubrication should be assumed F as 0.1 to 0.0 T, and the bearing used for moderate operating conditions with pressure is 50 to 100 psi, and the velocity is 50 to 200 feet per minute. Okay, yan. Yung discussion natin sa bearing. So now for the example, kasi meron tayo pinakita mga formula, gamitin sa example. Ito ang purpose ng example ko, di ba? Paano mo gagamitin yung mga equation doon? So, an 8 by 9 inch full bearing, so this is a full bearing, consider L over this one for table and charges only. Suppose 15 kips with N is 1,200 RPM. CR over R is 0.0012. Construction is medium heavy with radiating and convecting area of about 18 dl. Airflow about the bearing of 80 feet per minute may be counted on nearby pulley. Ambient temperature is 90 Fahrenheit. Decide upon a suitable minimum film thickness. A. Compute the frictional loss and the steady state temperature. Is additional cooling needed for a reasonable temperature? Determine. B. The temperature rise of the oil as it passes to the load carrying area and the grade of oil to be used if it enters the bearing at 130 Fahrenheit. And C. The quantity of oil needed. So sabi dito, ikaw muna mag-decide kung ano yung minimum film thickness. So, hanapin mo doon yung minimum. Ayan, by Norton. So given D, 8 inches, L, 9 inches, W, 15,000 pounds, in and 12 RPM, CR over R is 0.0012. The air velocity is 80 feet per minute. Ambient is, temperature is 90 Fahrenheit. Oil entering temperature is 130 Fahrenheit. Required A, the frictional loss in steady state temperature. B, temperature rise of oil. C, quantity of oil. Solution. So, kailangan natin mga in seconds. Length of S is 1,200 over 60 or 20 revolutions per second. R is equal to D over 2 for inch. CR is equal to 0.0012 D or this 4 is, R pala is 0.0048 inch. By Norton, H over is equal to 0.00025 D or 0.00025 times 8. Ang diameter natin is now equal to 0.002 inch. So, from table 8020, meron tayong S as 0.121. Paano yan? Table 8020, hanapin natin. Teka. So, dito. Table 8020. Meron tayong L over D as 1. Paano na po yan? L over D as 1. Hanapin natin. Table 8020 or table 1, full bearing. So, ang kailangan din dito is yung L over D is 1. Tapos, ano yung katabi? S. Yan eh. Equation 15. L over this one, hindi ko na nagay dito. CR over R is 0.0012. One. Hanapin natin yung may isa dyan, partner. So, dito na tayo sa L over this one. Wait, so, ito of S sub 02. Ito yung nakalimutan kanina. H sub O over C sub R is 0.002 over 0.0048 or 0.4. So, table 8020 o sa first one, ito, sa first. Dito sa lecture is table 1. Ang L of value natin is 1. Ang H sub O over CR is 0.4. So, look, doon makikita nyo yung S as 0.121. So, page 15. Yan. L over this is for full journal. So if yung problem na bago, naging 120 degrees journal, sa solution nyo, yung nakalagay doon na from table 8020, palitan nyo rin. Kasi pag nag-is kayo ng table 8020, para sa full journal yun, ang problem mo is partial journal. So mali ka na. Kahit isang yung word lang na yun. Okay? Sabihin, kinukupya ka talaga. Okay? Kinupya mo yung sa klase mo, di binago yung mga importante. Kailangan ma-edit doon. So, N over D is 1. S sub O over CR, 0.4. So, ito. So, ang value ng S mo is 0.121. P is 50.58. R over CRF is 5.79. So on. Nakikita yung mga value niya. Makikita mo naman dito ulit. Yan. Yan. So, yan. S is 0.121. Sommerfeld number. R over CRF is 3.22. Q over R CR NSL is 4.23. Rho C delta T sub O R divided by P is 14.2. So letter A, ano yung required? Nakasili ka ng minimum thickness. Gagamit mo na dito. Sa letter A, required is temperature rise. Next is frictional loss and steady state temperature pa na. Yan. So natin yung A, B, and C. So R, ano dito? Kailangan mo yung friction factor. Kasi kailangan mo ng frictional loss. Okay? So ano nyo? May term doon. R over CR times F is 3.22. So substitute mo yung values. 4 over 0.0048 times F is 3.22. So F mo is 0.003864. And the friction force is F times W is 0.003864 times 15,000 is 57.96 pounds. The velocity is pi dn over 12 is pi times 8 times 1, 2 over 12 is equal to 2513 feet per minute. The use of F, frictional force, energy is F times B sub M is 57.96 times 2513 is 146,654 foot-pounds. Then Q is equal to S sub C R A B T sub B. So S sub R is 0.108, S sub C is 0.017 times P sub A 0.6 over D is 0.4. So S sub C is equal to 0.07 times 80 is 0.6 over 8.4 is 0.103. Added 2, magiging 0.211.5 per minute square inch Fahrenheit. So, and A sub B is equal to 180 L is 180 times 8 times 9 is 1296 square inches. And then equate Q sub F as Q. So 14,145,654 is equal to 0.211 times 1296 times delta T. So delta TB is equal to 550 Fahrenheit. Is very high. So additional cooling is necessary. Matanong. Yeah. So P is the temperaturized oil. So, mayroon doon. Andito na. Rho C delta T sub O over P is equal to 14.2. Solve for delta T sub O. Ito yung required temperature rise. But the pressure is equal to W over DL is 15,000 over 8 over 9 is 208 PSI. Then 112 times delta T over 206 is equal to 14.2. So delta T sub O is 26 Fahrenheit. This is the answer as temperature rise. At anong oil naman gamitin mo? So, paano yon? So, T sub I is 130 Fahrenheit, T sub O is 156. The average is 1 half of 130 plus 156 or 140 Fahrenheit. Then the Sommerfeld number is R over CR squared at mu N S over P. Ito kasi mayroong mu. Sa mu na yan, makukuha mo yung viscosity. Yung viscosity, makukuha mo yung type of oil. So, S is 0.121 times 4 over 0.004 squared times mu times 20 over 8. So mu is equal to 1.8 times 10 negative 6 grain. Or figure EF 16 where mu is equal to 1.8 times 10 negative 6 grain and 143 Fahrenheit. Use the sa A10W. Figure na. Let us see what is the flow rate. Quantity of oil. So meron tayo doon. Q over R, CR, NSL is 4.33. Substitute values. Q over 4 over 0.0048 over 20 over 9 is 4.33. Therefore, Q is equal to 14.96 cubic inch per second. So, from one table, makukuha mo na lahat ng properties. Okay. So, this is the end of this topic, roller and ball bearing.